Hi there. I'm 17 and I'm about to give you I'm 17 and I'm about to give you a very basic explanation of what quantum superposition is in like 5 minutes. Why am I doing this, you may ask? Because you clicked on the video, so you signed up for it. Before I start, because I know some smart ass is gonna go into the comments and complain about the 2 things I got wrong in this video, I am in no way a qualified professional when it comes to quantum physics, nor am I claiming to be. I just find this stuff interesting and wanted to make a one-off video about it for the lols. Also, the visuals aren't supposed to be accurate representations of what I'm talking about, just visual aids to get my points across. Now with that out of the way, 3, 2, 1, go. Quantum superposition is a fundamental concept in quantum mechanics that describes how a quantum system can exist in multiple possible states at the same time until measured, interacted with, or otherwise observed. This phenomenon, though it technically applies to all matter, only really has observable effects on well-isolated atomic and subatomic scale systems. On large objects that are tangible to a human, like the ones we interact with every day, the effects of quantum superposition and other such properties become so small due to decoherence that they are essentially negligible. As an example of quantum superposition, it can be said in quantum mechanics that an atom can be in both an excited and ground state at the exact same time, or even in 2 different spatial locations at the same time. At first, this is probably a really confusing, almost impossible sounding notion, but it's possible according to quantum mechanics. This atom can continue to be in this variety of states at the same time until its state is measured or somehow interacted with, at which point its superposition is forced to collapse into one definitive state. To better visualize this effect, I'll go over 2 examples. First, imagine that you are flipping a coin. In this case, let's say that the coin has 2 definitive states, heads and tails. While the coin is in midair, its state is undetermined. When the coin comes back down, lands on either heads or tails, and is observed, it takes on one definitive state. In quantum mechanics, a system in superposition is somewhat like that of the coin, but with an important distinction. Rather than the system hiding its outcome like the coin in midair, a system in superposition genuinely exists in a combination of both possibilities, heads and tails, until it's observed. The second example I have is the famous Schrodinger's cat thought experiment. In this thought experiment, imagine a cat in a box with a bottle of poison and a hammer connected to a Geiger counter, which is a device that measures atomic radiation. There is a single radioactive atom besides the Geiger counter, and if it decays, the Geiger counter detects it, releasing the hammer which hits the bottle of poison and kills the cat. When it comes to radioactive atoms, they are in a superposition of being decayed and not decayed at the same time until measured, technically making the cat in this case alive and dead at the same time. Though this situation isn't actually realistic for a number of reasons, it's meant to serve as a demonstration of the confusing and contradictory effects of quantum superposition compared to classical physics. Mathematically, quantum superposition can be thought of as a linear combination of the possible basis states expressed as this, where alpha and beta represent complex probability amplitudes and psi represents the quantum state of a system. The probabilities of obtaining either outcome upon measurement are given by these respectively. To satisfy the normalization, these must have a sum of 1, therefore they equal 1. A famous example that demonstrates the noticeable effects of quantum superposition in the real world is the double slit experiment. The basic setup of this experiment consists of a wall with 2 spaced slits in it and another wall behind it. When light is shined through the slits, we would expect 2 distinct regions of light, one for each opening. Instead of this, we get an interference pattern characteristic of waves. Due to this, the experiment was a huge piece of evidence in proving the wave-particle duality of light. However, the double-slit experiment doesn't just work with photons. It works if a beam of electrons or other such subatomic particles are fired at the slits too. Here's where things get weird. If we fire enough subatomic particles one at a time, you would again expect there to just be 2 distinct regions that show up on the back wall. Instead of this, we get the same result, an interference pattern which accumulates with each fired particle. This effect is caused by the individual particle's wave function passing through both slits at the same time, thus putting the particles in a state of superposition between the 2 paths and allowing the individual particles to interfere with themselves. To make things even weirder, if we put detectors at the slits to determine which path the subatomic particle took, the interference pattern we would otherwise get disappears. Our new pattern looks like how we initially expected, just 2 regions of light. This happens because when the particle states are measured, the detector becomes entangled with the particles and forces them out of their state of superposition, creating a definitive state for each particle. That is an extraordinarily brief rundown of how quantum superposition works and what it is. I'm gonna go to bed now. Be cool, stay in school, eat your vegetables, make your bed, brush your teeth, and be a kind person. Okay, goodbye.